A very important property of functions is called the average rate of change. Now, obviously, a function, I have a graph here, just any general function, has some sort of change in the output or in the y values. Okay, so over a certain amount of x values, you have a change in the y. And so in this graph here, if you went from point A to point B, literally in the x direction here, the graph changes in its height, right? If you were to take this up, you would have a function value here. This would be f of a, and take b up, and you have an f of b. Now, the function is changing, but at different rates throughout that interval, right? So it's starting out a little bit slower rate and then starting to increase more. And really, I could have spread those out a little more so you could see that more dramatically. But essentially, the rate of change is changing throughout that interval from A to B. But the average rate of change is the overall difference from the endpoints. It really doesn't take into account what's going on in between. Okay? It's kind of like if you were driving your car and you were driving down the highway, and for part of that time you were driving at 70 miles per hour, and maybe you hit some construction and you had to slow down to 45 miles per hour. And then in the end, you get to your destination. Well, your instantaneous rate of change is what was being read on your speedometer. The average rate of change is simply taking into account the endpoints. It's how far apart the endpoints are and how much time it took to get there, and you divide them out to get your average rate of change. So it doesn't really take into effect it doesn't take into effect any individual instantaneous rates of change. It may take them all into account together, but in the end, you're really just focused on the endpoints. So here, the average rate of change, in a similar way, is just focused on the endpoints. It's, as a rate of change, it's how much it's changing per unit horizontally. So how much it's changing vertically per unit horizontally. Okay, and so to get that, you're going to be dividing the vertical change by the horizontal change. It's kind of a slope idea. In fact, if you could imagine a slope, you could imagine a line going through the 2 points at A and B, okay? And that slope would be the average rate of change. And so with a slope, I'm going to call this the ARC for average rate of change. That slope then is found by taking the vertical change divided by the horizontal change. That's always our formula for slope, the rise over run. So between those 2 points, you take the change, the vertical change, which would be the f of b minus f of a. That's the difference in the 2 outputs, okay? The difference in the 2 outputs, that's the distance here that the graph is increasing or decreasing if it was a different type of graph. Then in the denominator, you divide by the horizontal change, okay? Horizontal change in this case is b minus a. So you have the change in y's over the change in x's, which is essentially a slope again, okay? And so this formula is what you would have for the average rate of change. Now, if I wanted to give you something more specific, let's say I wanted to find the average rate of change I'll give you an actual function here. Let's go with the function, I don't know, let's go with x cubed minus 2. Alright, let's go with x cubed minus 2. And I want to do it over the interval. Let's go 1 to 4. So over the interval from 1 to 4, what is the average rate of change? Okay. Now again, average rate of change just takes into account the endpoints. The 1 and the 4 are basically your A and B from this diagram or from this graph. Okay. Now this function is not the function I wrote down here. It's something different. They're shaped similarly, interestingly enough. But yeah, so A and B are just the endpoints on this interval. So f of A is going to be important for our formula. That's just f of 1. And when I plug in the 1, you get 1 cubed minus 2 is negative 1, right? 1 cubed is 1, minus 2 is negative 1. Then you get f of b. F of b is going to be f of 4. So you take 4 cubed minus 2. Well, 4 squared is 16. Multiply by another 4, you get 64. So 4 cubed is 64. Minus 2 is 62. Okay? So I've got negative 1 and 62. And so I plug everything in now to my formula. So the average rate of change is going to be f of b, which is 62, minus f of a, which is negative 1, all over b, which was 4, minus a, which is 1. Okay? So I filled in my 4 values. Now I just simplify that. So that is going to equal 62. Double negative here is plus. So that's 62 plus 1 is 63. And then 4 minus 1 is 3. This is going to work out nicely. I made that up on the fly. It's going to work out. It's going to divide out nicely. 63 divided by 3 is 21. And so the average rate of change of that function over that 3-unit interval is 21. Okay, that means that on an average, the function is increasing 21 units for every 1 unit horizontally. Okay, so it's an average rate of change. Now, the actual function, the x squared minus 2, isn't always going to be changing at a constant 21 to 1 ratio. Okay, but in the end, from start to finish, it will achieve a 21 to 1 ratio. Okay, or a 63 to 3 ratio is really what it's doing. All right. Okay, so that's a kind of an overview of your average rate of change idea, and I think that example will be helpful. The main idea with this example, and really with any average rate of change example, is that you take the endpoints, plug them into the function to get 2 function values, and then calculate the slope. You subtract the function values on top, you subtract the endpoints of the interval on the bottom, and then divide it out. Okay, and essentially that will calculate your slope or your average rate of change.